So, recap from yesterday. So, we had an exciting episode of MacGruber yesterday. You guys came up with good ideas. So, the thing to do was to take the butcher's block on the frozen floor, push off the wall, and send it cascading into the door, right? Okay, so all Chromebooks need to be closed. Seth Wood?
All right.
Okay, and why did this work? Okay, here's what we got to get to the bottom of. You know that it works intuitively, but when you push against the wall, we said you did work on the butcher's block, right? The amount of force you exerted times the distance through which you exerted it was somehow you invested something in this butcher's block we called energy, right? Which sent it across the room to crash into the door and free yourself from the cold locker, right? Okay. So we wanted to explore this a little further, right? And we built a spreadsheet yesterday from the data that we took. Whoops. That data, right? And let's make that a little bigger. Okay, so what was this, right? First column was we had a basketball, and we dropped it over the detector, and we measured the height of the ball and its velocity, right, for a bunch of little samples. And looks like we got 6 data samples from the recorder while it fell. So this was, we just measured the mass. Mass doesn't change, right? The mass of the basketball was 1.324 kilograms. The position relative to the detector, these were the measurements from the detector, and we just said, okay, well, let's say that the lowest spot where we measured the height of the ball, let's just call that 0, right? Because what does it really mean if I'm measuring a height of a ball, relative to what? Relative to the desk, relative to the floor, it's all arbitrary, right? Question? It is, right. So it's just the distance, really the height of the ball, we're just measuring the height of the ball relative to some recognizable point. Usually it'd be the floor. We're just going to say, in this case, relative to the lowest point that we observed, right? Which was 0.949 meters above the detector, but who cares, right? We'll just say that's our 0 point, okay? So there's our height above the detector. For each one of those heights, we also measured a velocity, right? Why are the velocities negative here? Because it's coming towards the detector, right? If we wanted to, we could easily just make those positive and call them speeds. Should we do that? Let's do that. Let's call those. So, let's see. Oh, it's going to mess up my other. Oh, no, it won't. Okay, we're okay. All right, so those are, right, so then we ended up with these. These were the speeds in meters per second, right, for each of those positions, those snapshots in time, right? And so then we did some stuff. We measured, okay, well, this is just the weight of the ball, isn't it? Right? So maybe it'd make more sense for us to put the weight of the ball. Why don't we take this column and cut, and we'll put it, we'll paste right there. Okay, so there's the mass, there's the weight. Just to make our table a little easier to read. Okay, sound good? So we got height, velocity, and then we calculated the work that I did to raise the ball up in the first place, right? We'll come back to that later, right? But I had to do some work to pick this thing up from the 0 position up to where I drop it, right? Agreed? Okay, and then we calculated the work done by gravity, right? When we drop the ball and the ball falls, gravity is pushing it down in the same direction that it's displacing the ball, and so it's doing work, right? So really all we did to find the work done by gravity, all we had to do, we'd already done some math here, we just subtracted this much from these values, right? Does that make sense? Okay. And we could have easily just said, let's find out how far it's fallen from its highest position times the weight, and we would have gotten the same results, right? Just pretend we did that, right? So we're just saying how far did the thing, how far has it dropped being pushed by the weight? Okay, but here's the question then, what we want to do. So we pushed this ball up to here, and we could have set it on a shelf, or we could have suspended it from a string or something, right? So we put it up into that position, and really the part that we observed is where we cut the string and the ball falls, okay? So we did something, and you guys called it something. So what did you call that when we do some work against, what did we call it?
Potential energy.
Okay, we give it some stored potential energy, right? What does potential mean? Potential means it could be realized, right? There's something there that's available, right? If we cut the string, we can release that energy and the ball falls and it kills a mouse or something, right? I mean, it does some work for us, right? Maybe it drives a nail into a board. Who knows? It does something useful for us, though maybe, right? But we put the ball up there and imbued it with this potential energy, and now it's just sitting there. Now let's focus on the part where we release it. As we release it, the energy that we've invested in it is going to be returned to us by gravity, right? That's what we did with the floor thing, right? But there's got to be something that's measurable about the ball, the energy that it's accumulated. We shouldn't have to think about how far gravity's pushed this thing. We should be able to come up with some way of describing the energy based purely on the characteristics of the ball, its mass and its speed. Yep.
Can something have 0 potential energy?
Sure. Anything does. I'll tell you right now that, ask me about an object. Like that fan right there?
Sure.
Yeah, call it 0. That's fine.
But doesn't it have the potential to move?
It does. So how about right here? That's got 0 potential energy right there.
Yeah.
If I want it to, it's fine. I can call that 0. Or I could call it 100 joules. Or I could call it 1,000,000 joules. Or I could call it negative 100 joules. They're all correct. It doesn't make any difference because potential energy is completely arbitrary. All that matters are differences in potential energy.
Technically, each object has limited potential.
Well, technically, each object could be the potential, the gravitational potential energy in an object is purely based on where you're considering the height to be 0, right? So if I say the height is 0 here, and I pick it up 1 meter, now I've given it some positive potential energy, right? But I could say, well, let's let this equal 0 height, and it started off at a negative height. So it had negative potential energy, and now I made it 0. Doesn't make any difference. The difference between the potential energy here and the potential energy here is the same, and that's all that matters, right?
Yeah.
So, we haven't really talked in great detail about gravitational potential energy. Today we'll come up with a formula, and then we can answer that question a little bit better, right? But when we pushed the butcher block against the wall, and I keep losing my pen. There it is. When we pushed the butcher block against the wall, what happened? So we gave it something, and now it's moving. We're not doing anything anymore, right? It's just sliding across the floor, but it's got energy. How do you know it's got energy? It's moving, right? So there's got to be some formula that's going to be that we're going to have access to we're going to be able to use to calculate how much energy it's got. Is it enough to break the door? We should be able to tell by just knowing what the mass of the block is and how fast it's moving, right? Similarly, we ought to be able to say when I drop this ball right there, at that point right there, it's got, if I know what the velocity is, and I do on my table, I should be able to calculate what the energy is, right? See if we can come up with that. Okay, so let's focus on the path down, right? On the path down, right, on the path down, we know what the velocities are for each height, because that's what the detector told us, right? This fancy detector records all this stuff. Okay, so let's look at that. So here's the basketball. Oh, that's not basketball.
Can we get a snowball?
Right. There's a basketball. Okay, and the basketball is going to fall from there down to
She's just done.
there, right? Okay, where would it be convenient for us to calculate? Well, okay, let's just say, let's say that we're going to measure the center of mass right here. There's the center of mass. Let's just say this is going to fall through some distance delta y. Okay, so it's going to fall from there down to there through some distance delta y. Delta y, not y. That's our displacement. What's the force acting on the ball?
Gravity.
Okay, so what is that force? Well, just say
MG.
mg, right? G will be 9.8. So it's, the force is acting in this direction. The force is mg, right? And so what's the work being done by gravity then? Yeah.
Wait.
mg delta y, right? Is the work done by gravity. That makes sense? Okay. Okay. So can we come up with a way of describing this kinematically in terms of one of our kinematics equations? Can we meld this with a kinematics equation? So in general, in this case, the gravitational the acceleration is due to gravity, but more generally, the work done is going to be equal to the mass times acceleration times a displacement. In this case, we'll call it delta y because it's vertical, but it could be delta x or delta s, right? Did we have a kinematics equation that used some of this information? Think about our kinematics equation. We only had 4 of them. One of them had a displacement in it though, didn't it?
Acceleration equals
You're thinking about, it's the one without time, isn't it?
Yeah.
Right? 4. It's number 4. Yeah, what was that one? V squared minus V naught squared equals,
1/2. Was it?
No, it was 2 acceleration delta.
Oh, yeah, 2
delta s, but in this case, we'll call it delta y, how about, because our movement is vertical, right? So for vertical motion, it might look like that. Well, look right there. There's an a delta y, and there's an a delta y, right?
So m equals 2.
Okay, so if we wanted to isolate that, all I'm going to do is just divide each side by 2, right? Okay, so then we end up with v squared minus v naught squared over 2 equals a delta y, right? Now let's do something kind of weird here. Let's just split this into separate fractions instead of having a common denominator. Let's write that as v squared minus v naught squared, each of them over 2, equals a delta y. Okay, and let's make a substitution, right? Let's substitute in there. Okay? So the work that's done here then is equal to m times v squared over 2 minus v naught squared over 2, right? Okay, well, if I distribute the m, and let's pull the 1/2 out front, so how about if we just write that as 1/2 mv squared minus 1/2 mv naught squared? Does that make sense?
Like not squared?
V sub 0?
Yeah. You said like,
Yeah,
yeah.
V not squared.
v sub 0 squared. Okay, so then that's telling us something, right? Isn't this a characteristic of the object at the end of the descent? And this is a characteristic of the object at the beginning of the descent, because m isn't changing, but the velocity is. Speed's really all we need, doesn't have to be velocity in this case, just speed, right? This is my initial speed and that's my final speed. So this must be something, right? The work that's done by gravity there is gonna be equal to the difference between the final value of this quantity and the initial value of this quantity. What must that quantity be? Let's take the example where the ball is starting from rest. So if the ball is starting from rest, that term goes to 0 because the initial speed is 0, right? So the work that's done by gravity then, if this thing is falling from rest, is just 1/2 mv squared. That's what we were looking for, wasn't it? That's a measurable quantity that's related only to the parameters of the object, right? Its mass and its speed. What should we probably call that? Yeah, right, that's the energy of the motion, isn't it? So that's the kinetic energy, right? When we push the butcher's block off the wall, what did we give it? Well, kinetic energy, right? We pushed this thing, and it's got a mass, right? We did some work by exerting a force on it, we gave it some speed, and so now it's got a kinetic energy that's given to us by that formula, 1/2 mv squared, right? And that's the amount of energy that's going to carry into the door. Yes?
So work equals kinetic energy?
Okay, so now we're getting somewhere. Now we've got to answer the question. So how is the work related to this? The work that was done is what caused a change in kinetic energy. If it starts from 0, then there's a 1-to-1 correspondence there. But what if the ball was already moving a little bit? Like let's take a different example. Let's take an example of something like a butcher block on a frictionless surface, right? So if I'm pushing, we could use this card.
Break the door open.
With right? Chromebook card. So if the Chromebook card is at rest, and let's pretend it has frictionless bearings and the whole bit. If I push on this thing with a certain force through a certain distance, off it goes, right? And the amount of work I did on it is equal to the kinetic energy that it has after I'm done pushing. Okay, but what if this thing was already coasting down the hall at a little bit of speed, and I push on it a little bit more through a distance?
So work is the change in kinetic energy.
Right, so the work done is the change in kinetic energy, isn't it? Right? It already had a little bit, but the work that I did by pushing on it, it determines the change in the kinetic energy. How much extra kinetic energy did I give it by doing that work? Right? Does that make sense? Okay? All right, so now let's take this one step further. In reality, this is not at all frictionless, right? Does that make sense? So if I were to, like, let's say I'm pushing this thing down the hall at constant speed. I have to push the whole time because there is a little bit of friction, right? So what are the two forces acting then? Friction's acting against the direction of travel, and my push is acting in the direction of travel. Be just like a car with its cruise control on, right? If a car's traveling down the road with its cruise control on, is it using gas?
Yes.
Yeah, definitely, right? Because there's a significant frictional force it's overcoming. There's the driving force and the frictional force, and they exactly counteract. So,
We had a frictionless car.
frictionless car wouldn't be very useful.
Do you not do that?
We don't know if we had,
Well, if you start pushing it and then you jump on.
okay, yeah, if we had a.
But the wheels still have the.
Yeah, okay, what if
The
when you
types
get
of
the
the
wheel,
wheel, they just retracted, like, you mean, like maglevs. Wouldn't that be like the best gas knowledge ever, because you only have air resistance?
Yeah. Yeah.
It requires a lot of
Then
technology.
you have to put them down every time you want to.
Yeah.
I mean, it's constantly technically.
Okay, so let's think about that example with the cruise control though. What's the change in kinetic energy there? If we're traveling down a straight road, well now just think about it without even looking at the forces. The speed, if it's on cruise control, what can you tell me about the speed? It's not changing. Is the mass of the car changing? No, right?
I mean, it might be.
It's possibly very slightly, but negligibly so, right? So the mass of the car is staying constant, the speed is staying constant, so the kinetic energy is staying constant. So Seth, in answer to your question then, does the force cause the change in kinetic energy? Yeah, but explain this one then. Why is it that the driving force, I'm pushing on this thing, but it's not gaining any kinetic energy? Well, it is moving. It's moving down the road at constant speed.
If you add speed to it, it has more kinetic energy, right?
Well, but it has a certain amount of kinetic energy when I pass point A. Say it again.
It's losing energy from the friction.
Okay, because there's not just one force acting on it. With the ball falling, there was only one force acting, which was gravity, right? With the car moving down the road with its cruise control on, how many forces are acting along the direction of travel? Two. There's the driving force, which is acting in the direction of displacement, and there's the frictional force, which is acting in the opposite direction.
But if you hit it and you're moving at a faster speed, you increase its speed.
Sure.
Then you're adding kinetic energy.
Right. Right. Okay, but let's take the example when the cruise control is on for a second, though, right? So the work being done, the driving force is doing positive work on the car, right? Pushing it down the road. But if the driving force and the frictional force are equal and opposite, the frictional force is doing what kind of work? If it's pushing in this direction, but the displacement is in that direction. We could do this in terms of our fancy equation if we want to. Right, what's the work equation? Right, work equals force times displacement times, I'm forgetting something. It's a dot product, right? It's actually force times displacement times cosine theta, right? Because remember what it is, it's force times, we've done that one, haven't we?
Where did that come from?
Oh, we not talked about that one yet?
Maybe.
Okay, I think we did, but very briefly.
Yeah, I think you like Boston.
Yeah, right, because like when we're pushing it up a ramp, for example, right, we're only going to take the component of displacement along the lines of force, right? So for example, I think what we did, what we talked about in class was something like this, right? Like if we had a guy, he was pushing it up a ramp, right? That was the deal. Where we ended up with,
Oh, no, I remember.
right, if this guy is, if he's pushing in this direction and it's sliding up the ramp, then he's doing work on it, but how much work is being done against him by gravity, right? Well, gravity's, very little of this motion is along the lines of force vertically, right? See what I'm saying? Okay? So, right, only the component of the force that's acting along the direction of travel, or you could think about it as only the displacement that's acting along the lines of force is the part that's contributing to the work. So if for example, if the displacement is in that direction and the force is acting in that direction and that's theta, not all of the force is doing useful work, right? Only the part that's acting in the direction of motion is doing useful work, right? So we'd have to break this force up into components, and we're only going to take the parallel component of force. The perpendicular component's doing nothing. Just like, remember we said if I carry an object at constant speed horizontally, am I doing any work? No, I'm not, because the force I'm applying is in this direction and the displacement is in that direction, right? So I'm not doing any work when I do
Are
this,
you
right?
also applying a force forward though?
Well, but assume that we're starting the camera right now.
Okay.
It's already moving, right? Because technically to accelerate, I'm doing a little bit of work, but then I'm going to get that back when I decelerate it, right? So the net result would be 0, right? Okay? So to simplify this, all we have to do is take force times displacement times the cosine of the angle between the vectors, right? Okay, so then why do we bring this up? Okay, so we brought this up because,
We just forgot where the cosine came from.
yeah, where the cosine came from, but we were talking about the situation with the car. Where did I write my fancy equation?
At bottom.
Right there. Right, so what about the frictional force? We've got the displacement in this direction, and the frictional force is acting in that direction, and what's the angle between those vectors? 180. What's the cosine of 180?
1.
No,
Negative 1.
negative 1, right? So the friction is doing negative work, right? And the friction is doing an amount of negative work that's equal to the positive work being done by the driving force, and so the net work being done on the car is 0,
That's just
right?
relative, right?
Say it again.
Like the negative is very relative.
Well, it's a real
We're saying the
thing.
driving force.
The driving force is doing positive work, the frictional force is doing negative work, and as a consequence, the car is, no net work is being done on the car. So when we talk about a change in kinetic energy, it's not just the work being done, we gotta be more specific. Now let's take one more example. Let's say this time that the driving force on the car is 1,000 newtons and the frictional force is 500 newtons. Say it again. There's going to be acceleration, you're right. We don't even have to worry about acceleration so much with energy, though. That's what's nice. We can just think about it in terms of these quantities that are not vector quantities, right? So we've got what's the work being done. Let's say, so we're applying 1,000 newtons of force through 10 meters. In that 10 meters, how much work is being done on the car by the driving force? 1,000 newtons, 10 meters, 10,000 joules, right? Okay. How much work is being done on the car by the frictional force? 500 newtons, 10 meters,
Being negative.
negative 5,000 joules of work. So what's the total work being done on the car? 5,000 joules, right? So how much kinetic energy do you suppose is being imparted? How much is the kinetic energy increasing then over that 10 meters? How much? 5,000, right? Because 10,000 joules of positive work is being done, 5,000 joules of negative work is being done for a net work of what? 5,000, right? So that's what's responsible for the change in kinetic energy is the net force, right? The sum of all the forces. So we can only increase the kinetic energy if there is a net force. Makes sense, right? That totally is consistent with the stuff that we learned when we talked about kinematics and dynamics with forces, right? What was responsible for an acceleration? Billy pointed out there was an acceleration. What do we have to have for there to be an acceleration? The net force, right? If there's no net force, there's no acceleration. It's going to be, everything's in equilibrium and the velocity doesn't change, right? Only if there's a net force is there an acceleration. Only if there's an acceleration could it pick up speed and therefore kinetic energy, right? So the work energy theorem, here's one part of the work energy theorem. This is really simple. This is a lot easier than the way we did this last time, isn't it? We don't need any fancy kinematics equations or dynamics, free body diagrams. All we got to know here now with the work energy theorem is that the work due to the net force, so call it net work, equals change in kinetic energy. That's it, right?
Yeah.
Okay. Make sense? Okay, let's look at our spreadsheet again. We can do something pretty cool with the spreadsheet. So, yes, we can.
You can do everything.
So let's make another column here where we're calculating the kinetic energy of the ball as it falls.
Can a potential energy be a negative or no?
So kinetic energy. Say it again.
Can a potential energy be in a negative?
Sure.
Okay.
Yeah. Can kinetic energy have a negative value?
Yes.
Yeah.
It all depends on control.
No. The answer to that is no.
Why not?
Because kinetic energy does not depend on, it only depends on speed. Can speed be negative?
No.
No. Can mass be negative?
No.
No. Kinetic energy is 1/2 mv squared. If an object is moving, its kinetic energy is positive. What's the lowest it can be? 0, if it's not moving. It doesn't matter what direction it moves, because energy is, thankfully, not a vector quantity. It's a scalar quantity. It's independent of direction. If I move 1 meter per second in that direction or that direction or that direction, my kinetic energy is the same in either of those cases, right? Okay? So let's make a column that calculates kinetic energy. So what's my formula going to be? So I'm going to type equals to get a formula going here. What am I going to type? Okay, so 0.5 times, that's my mass, right? Times my speed is right there. Everybody agree?
We do
Squared.
final,
Say it again.
will we do final velocity?
I'm doing the velocity, the speed, I should say speed. The speed at each instant that we recorded a result,
Oh.
right? So we're going to be tracking, so we're calculating the corresponding kinetic energy. So there's the kinetic energy at when the position was a height of 0.182 meters and the speed was 0.34 meters per second. Okay? And so let's just drag that formula down. And those are my kinetic energies. It's increasing. How come? Yeah, it's picking up speed as it falls, right? Okay, so now let's think about another part of this. So we got the idea of kinetic energy. What about this notion of, we had this stored energy, right, that we call potential energy. That was based on how high I picked the ball up. Now here's a very important question, Seth. So you got to close that up so you can see this important question. Does it make any difference? I'm going to take the basketball and I'm going to hang it up right here from a string. Okay, it starts right here. I'm going to pick it up and put it there. Okay, does it matter if I take it through that path, or if I am really feeling fancy and I'm doing all kinds of dipsy doodles and behind my back and all kinds of things, and I stick it up here? Does it change the energy?
No.
Doesn't change it at all. It's independent of the path that I took, right? If we're saying that the height that it was at initially we're calling 0, and we're going to move it up 1 meter, let's say, it does not matter at all which path I take it through. It ends up with the same amount of potential energy regardless, right? Okay, that is the hallmark, or the one criterion that's necessary to call a force conservative. So that means that we're doing work against gravity. That means that gravity is a conservative force because it's independent of path. Does it seem like all forces would be that way?
No.
They're not. Can you think of an example of a force that's not that way?
Magnetic.
No, magnetic is conservative. Here's one though. I've got this object right here, and I'm going to slide it to there. Okay, here's one path. I did a certain amount of work, right, against friction. Okay, did I do the same amount of work this time? Quite a bit more, because the path was longer. I had a longer path to push against friction over, right? So that's a non-conservative force. It's definitely dependent on the path that I take, right? But it doesn't matter with gravity. Makes no difference. It's a conservative force. Okay, because it's a conservative force, we can come up with a really easy formula. It doesn't matter how far I move this thing vertically. All that matters is how far did I offset it, horizontally. All that matters is how far did I offset it vertically, right? Okay, so how much work am I investing in this then? The mass of the ball times the acceleration of gravity is the force that I have to use to overcome gravity, right? Okay. The displacement vertically is the only part that matters. That's a pretty easy equation, right? So then what does that tell me that my formula for gravitational potential energy is going to be? You can come up with it right now. It's just the work done against gravity, right? So that's going to be the force times the vertical distance through which I push it. So it's just mgh. That's it, right? Now h is completely arbitrary. We have to agree on a set reference value for h. Like we're going to say it's the top of the desk or it's the floor, right? But once again, it doesn't really matter which one we pick. All that matters is how much is the gravitational potential energy changing. Because let's do a little experiment here. You make a prediction for me. If I calculate the gravitational potential energy of the ball on our spreadsheet as it falls, can you make a prediction about how the gravitational potential energy and the kinetic energy are going to be related?
Potential energy decreases is going to
Okay, they're going to be the same, except you're right. What does this mean? You're right.
So
Flip.
signs.
as kinetic energy increases potential energy.
Okay, so the sum of the two would be what? Well, it might be, but the sum of the two is going to be some constant value. Agreed? That here it's all potential and zero kinetic. As the ball falls, it's giving up gravitational potential energy, but it's picking up a corresponding amount of kinetic energy. Right? Does that make sense? Let's just see if it works. So this is just the data we took in class. Let's make another column here that's gravitational potential energy. Okay? So that's going to equal just mgh, right? Okay? So that's equal to that mass times g times height. And we actually already have that column, don't we? It's right there. It's the work that I did to pick the thing up. So the combination of, oops, what happened there? There we go. So the combination of my kinetic energy and my, that looks dorky, my potential energy is what we call total mechanical energy. So I'll call that ME. Let's find the sum of those two. This plus this. And what do you find?
It's just about the same.
It's pretty constant. Does it make sense? Is this just crappy equipment, or does it make sense that the total mechanical energy is actually decreasing a little bit? Can you explain that? Ah, okay, yeah. Because there is some work being done against the ball by air resistance, right? If we did this in a vacuum, those should be exactly the same every time, right? But so what's the result of that? If we had a really sensitive pair of night vision goggles and I drop this ball, what would you notice in the room? Would you notice anything if it's ultra sensitive to changes in temperature? What would you notice? Yeah, the air around the ball would get a little bit hotter, right? Because it's starting to move and it's giving up a little bit of energy, right? So as it's resisted, it is losing a little bit of energy, and it's giving that up to the room, right, through the air molecules. Okay.
Well, how much does shooting a bullet increase the temperature of the air?
Well, a lot, but it's spread out over a huge region, and so you wouldn't really notice it.
I know war zones, did you actually raise the temperature?
No. But it's, I mean, it'd be much more heat liberated just when you explode the shell.
How much would the Earth's temperature decrease if every single animal died?
If every single, not much at all. I think it'd be not noticeable. You couldn't measure it.
Well, we couldn't measure because it would be dead, so.
It's true. That's true. It's a good point.
Like 2 or 3 years ago, there was someone who claimed that global warming is due to the fact we had like a lot of population.
That person's
And that we're getting closer to the sun every year.
that person's not very smart. It's I mean, honestly, I don't want to wade into any of the politics here, but you guys are smart. You're just so you know this. So you don't, you're going to go to college and you're going to interact with other smart people. Anybody, and there's not a lot of people that do, but anybody that really has a reasonable clue about science knows that the climate is changing. It's not something that's even up for discussion. There are 10,000 qualified scientists on the international consortium of people on the committee that collaborates to look at climate change. And how many of those 10,000 understand that there's climate change? 10,000. Yeah. It's not 9,009, it's 10,000. And it's so simple to explain. It's not like it's anything really that complicated. It's just, the greenhouse effect. We'll do a demonstration in here this spring. That's one of the things I really want to do. Does anybody have infrared goggles? I mean, night vision goggles?
Both would be cool.
Do you have some?
I might.
See
My
my
scope.
scope.
I might. I don't know for sure.
So anybody else? Yeah. So possibly. I mean, if you could find one, it could be just like a scope or something. But I mean, something that's that's night vision, which is infrared. All that is it's just converting the infrared part of the electromagnetic spectrum into visible spectrum for us, right? That's all it is. So when you look, anybody ever looked through night vision stuff? What do you see at night?
Vision.
You see vision, but what are the things that show up as being bright?
Bodies.
Things that are warm. Yeah, things that are warm. It's heat, right? So you can see heat. I can tell you right now what you're going to see. If we take something like an aquarium, and let's say we want to look at something in the aquarium, right? Something inside the aquarium, you can see it with or without the night vision goggles, right? But if we light a match, if we close the aquarium up and we light a match inside the aquarium, we can still see it visibly without any problem. But what's going to happen when you look through the night vision goggles?
Maybe brighter.
It's going to get opaque. You're not going to be able to see it after a while. How come?
Too much.
It's not the heat. It's the fact that there's CO2 in the tank, and CO2 is opaque to the wavelength of infrared light. So I can explain to you here in 5 minutes why anybody, so if anybody ever wants to know, scientists can't explain this stuff, it's not complicated at all. This is it. This is how it works. It's very simple. When there's energy incident on the Earth, here's how global warming works, the greenhouse effect. It's all just the greenhouse effect. So when energy is when energy is incident from the sun,
It just bounces in.
it warms up the planet. That's all it does. It warms up the planet, right? But it's coming in at all wavelengths, including visible. When the planet acts like a black body radiator, when it re-radiates the heat, it radiates it at a much lower frequency. So the energy that's radiated back up is going to be much redder. In fact, it's infrared. And the CO2 in the atmosphere is transparent to visible light, but it's absolutely opaque to infrared light. And so that light then gets reflected back into the planet by the clouds, and so it gets trapped. It's really simple. So if you raise the level of global CO2, you are going to, without a doubt, it's absolutely simple science, you're going to increase the temperature of the planet.
So with more people means more CO2, so more people are increasing. You
True.
just proved him right.
True, but the amount, and there actually is, people aren't such a big contributor, but there is a noticeable contributor. Bovines fart so much that they actually do contribute a really small percentage, but if you killed all the cows, that would affect a bigger change than killing all the people. Because the cows
So,
Oh,
fart so much.
All the
cows.
Yeah.
all the humans on the earth don't fart as much as cows.
But still, that's
They got 4 stomachs. They got-
where does 99.9% of that CO2 come from? Just from internal combustion engines, right? And that's easily measurable. If you look at like ice cores and glaciers,
Kill all.
you can capture samples of gas from any time period that are completely pristine, and so you have a record of the global CO2 content, atmospheric CO2 content, going back for hundreds of thousands of years. So it's so easy. to
How was
prove.
it
I
in the
mean,
Black Ages?
Like none. Like 6 cows. They weren't smart then.
Well, we don't have. Let's go back to. Yep. Back to Cooper. Back to Mr. Cooper.
Oh yeah, what are we doing today?
Hold on. We are doing a little more review.
Like,
Good. Break.
oh, what's it?
Not even that, it's just a good, a nice hard twist in your keyboard.
That was a little bit windy.
Dude, you come up those stairs, we're just winded.
How you guys win?
Shut up, Noah. Yeah, shut your mouth.
Feed your chickens.
Yeah.
Hey, Sonia.
Your chickens.
Oh, Rochelle. Hey, what's up?
Yeah, bro, that thing was fucking you.
No, I was ready to, I can grab it by the neck.
Hey, quiet down, you guys. Shh. Say that again, please. Oh, okay. Yeah, that's fine if she comes up here. Yeah, no problem. Okay. Uh-huh. Bye. No, we don't have Chromebooks. So we're gonna do a little review.
Nope. No me gusta, mi amigo.
Oh, I said Fortnite space.
Who are these random numbers?
Probably the same numbers calling you about my 7.
That's what I like that one.
Like 2 or 503s, and I don't have any voicemails.
I have 855, 509, 503, 541, and a 509.
I'll be able to see it.
A what? Yeah. What are the numbers?
Last one.
Did you recommend?
This is for you.
You're gonna call those an hour, aren't you? He gave that to you, I was like, what? It was on the wall, it was good. This is real. I was very trying to. Let's go give it to him. This is beautiful.